Hello everyone, this is the theoretical part of Lab 9, coefficient of thermal expansion. The target of this lab is to measure the experimental values of the coefficient of linear expansion for three different metals, copper, brass, and aluminum. So in this lab, we are dealing with a new branch of physics, which is the thermodynamics. This branch study and deal with the application of thermal energy, which is the internal energy of a system. The most important quantity in this branch is the temperature. So the temperature is simply defined by the degree of sensible heat or cold, and it's a scalar value. You have different scales like to report the temperature. But the most important thing is that the temperature depends on the motion of the particle. We know that all the matters are made up of atoms, and these atoms are allowed to move or to vibrate or to oscillate. So the motion from the atoms will give the object energy. So the motion of the atom will increase the energy of the object, or the energy provided into the object will allow the motion of the atoms. So this is what we call the kinetic theory of matters. Let's take the three different states of matter, the solid, liquid, and gas. We know that in solid, the atoms are not allowed to move freely, but they can vibrate, okay? While in liquids, we have flowing atoms, and in gas, the atoms are allowed to move freely. So as the temperature increases, the motion can say that the motion will increase. We have like a greater motion, and if the motion is very important, also the temperature of the system will increase. So the motion is related to the temperature. Why? Because we know that all gases, liquids, and solids can expand when their temperature increases. What do you mean by expand? We are saying that the solids vibrates, or we have flowing atoms, or the atoms can move freely. So by moving, we are increasing. If we take two atoms, so by increasing the temperature, we are considering that the distance separating the atoms is increasing. That's the simple definition of the expansion. And because the motion is related to the temperature, so it's a thermal expansion. So the expansion is due to the application of a thermal energy. A thermal energy is the variation in the applied temperature. If we take the example of the bridge, if you have like checked how the bridge are built, they are formed from short segments instead of having one long segment. We have like short segments. Why they build the bridge this way? Because they are trying uh, to reduce the effect of the expansion, or to prevent the expansion. If we consider that we are going to have an expansion, okay, by increasing the temperature, in this case, we are going to break the bridge. To relate this, take the example of the jar. So a jar is formed from glass, and the lid is formed from metal. Now let's say that you are trying to open the jar. It's a block. The easiest thing to do is to put the jar under hot water, and then we can easily open the jar. Why we can easily open the jar? Because we have an expansion. Now, why we have okay, we have expansion, but why we'll be able to open the jar? Because we have two different materials, the glass and the metal, and we have a difference in the behavior while applying the temperature. So we are going to see that all the matter, all the materials are allowed to expand or to contract, but in a different way. So we have a like a parameter, a coefficient controlling this expansion. So we can easily say that here the metal, the lid, has expanded more than the glass, and that's why we are easily able to open the jar after putting it under the water. So here, let's focus on the linear expansion. Okay, we know that the expansion will have place in 3 dimensions. Okay, but the linear expansion, it's like we are focusing our work in one dimension. So all the object will change the size with temperature. For a change of temperature delta T, we have a change delta L in the linear dimension. And delta L is related to delta T by this expression. Delta L, it's equals to L, which is the initial length of the material times alpha. Alpha is the coefficient of linear expansion and depends on each material. So for each material, we have a different coefficient of linear expansion. And that's why here we were able to open the jar, because we don't have the same coefficient for the glass and the metal. To prove this, let's take the example of this strip, which is formed from two rods, steel and brass, and they are stick together. Okay, at the beginning they were at room temperature, at the reference temperature. Now, by increasing the temperature, we are going to have a linear expansion. Okay, so a linear expansion, if the two rods were not connected, so the length of the brass will increase horizontally. Also, the length of the steel will increase horizontally. Now, because we have a difference and they are like stick together, we are going to have this bending. Now, if we check the bending here, we are sure that the steel has a greater linear expansion. So if they have the same length and the same difference in temperature, okay, why the steel has a greater delta L, a greater linear expansion? It's related to alpha. So delta L is here directly related to alpha. As alpha increases, so the greater the coefficient of linear expansion, the greater the difference delta L, okay? So if we take here, if we check the table for the brass, the aluminum, and we are using the copper, I think. Okay, we have different linear expansions, different coefficients. We are going for the three different metals to study the linear expansion. So for which material do we expect the greater value of delta L? Now, regarding the experimental setup. Okay, so here you have like a figure summarizing the setup. We have a heater. Why do we need the heater? Before talking about the heater, here it's in a color close to gold. You have a rod of copper. Okay, so here it's the rod of copper. We have an insulator here. Why we have an insulator? In case we need to like touch the setup. Okay, our target is to have a linear expansion, so to increase T. Okay, so here it's for safety. As you can see here, you have an indicator. Now in our lab, we used a analog one, not a digital one, but it's the same procedure. This indicator will measure directly delta L, the shift in the length. Now, instead of measuring T, we are going to measure R. But we know that we have a table summarizing the equivalent value of T for each value of R. So instead of measuring room temperature, we are going to measure the resistance before starting the setup. So the resistance should be, the room temperature should be somewhere between 20 and 21. So here we have the values of the resistance. Now what we are going to do, we are going here to add in the heater water. And as you know, when T is greater than 100 degrees, we are going to have evaporation in the water. So the steam or the water vapor will pass through the rubber tube and then will emerge into the metal. We are going to have thermal exchange between the steam and the metal. So the temperature of the metal will increase. How do we prove the increase in the temperature of the metal? By measuring R. If you go to the table, as R decreases, T will increase. So we are going to record another value of R, a smaller value of R. This value of R will give us T final or T hot. Okay, so as you can see, we are able to measure the length of the road. We are able to measure delta L, also delta T. So the target, or we can like easily get our target, which is the calculation of alpha. So here's the table. You have the data. So these data are the ones collected from the lab, the length of the road, the room temperature, resistance, delta L, and R hot. Now, from these, from R hot and R room temperature, we'll be able to calculate T room temperature and T hot, and then delta T for 3 different materials. And then you'll be able to obtain alpha copper, alpha brass, and alpha aluminium for the 3 different materials. Now, if you check the expression, what do you expect the value of alpha would be? Okay, so based on the expression. And then to compare your experimental value to the expected one, you use this table. So we have the expected value of the coefficient of linear expansion for aluminum, brass, and copper. You are going to compare it to the obtained one. Okay, and of course, don't forget to report the error on alpha, the error on alpha copper, alpha brass, and alpha aluminum. Now, regarding your lab report, so first you need to fill the table. Don't forget to add all the errors. Now, what are the units of alpha? Okay, based on the equation, what do you expect the unit of alpha would be? Calculate the error, the coefficient, and compare it to the theoretical value. Compare, so you need to use the percentage error. You find the percentage error. Now, based on your answer, okay, speculate the possible sources of error. So you need simply to list the sources of error. How might you improve the accuracy of the experiment? So here you need like to write about the possible ways to reduce this shift in the difference. Okay, يعني, for example, to measure the temperature directly, to isolate the system. Okay, so based on the experimental procedure, you are going to watch the experimental video, and based on the experimental video, you are going to deduce the sources of error and how can we improve this experiment to improve the accuracy. Now, if we compare the 3 coefficients, okay, compare the 3 coefficients, which in a coefficient of the copper is greater than coefficient of aluminum, or which one is greater, and interpret your results. So you need to think, if we increase alpha, what do we expect? So for the material, it has greater coefficient, linear coefficient. What do we expect? Also here, explain how linear expansion of metal rods can be used as thermometer. We know that the thermometer measures the temperature, the difference in temperature. So if we can use metal rods, how can they be used? And also the problem with this method. So the metal, based on the metal, can we easily use the metal as a temperature indicator? So it's one of the questions that you don't like. You need to think about it. Now, must material expand when heated? What can you conclude about alpha for materials that contract when heated? For example, if we take water, if it's at the solid state, if it's ice, it will contract first. So what will alpha be if we have a contraction instead of expansion? Another interesting question is when a mercury thermometer is placed in hot water, the level of the mercury initially drops before it begins to rise. We know that mercury is a kind of metal, so we should have an expansion. Now, why the mercury thermometer will drop first? I can give you like a hint that you need to know that the thermometer, it's not only formed from mercury. We have a tube of glass, and inside the glass we have the mercury. Okay. So also think about it. Now another. Let me erase this. Now, if we take here, it's a direct application. You have a steel bridge. You have the length, the difference in temperature. You have the value of thermal coefficient of the steel. You do the calculation. Now, for a slab of concrete used in highways construction, you have the like the ambient temperature, and also we have the length. Okay, now you need to calculate the minimum gap required between the concrete slab if bucking is to prevent. So it's similar to the example of the bridge, but now with values. So imagine that you have two parts. You know the length of each one. Okay, and by using the delta T, you have like the maximum temperature reached, which is 55 degrees. You have the ambient temperature, so you'll be able to directly obtain delta T. So you need to find this gap to prevent the bucking. So to not obtain like a cracks or to not break the road on the highway, we need to have a gap between the slab, because the slab will expand. Okay, so calculate only what you need to do to calculate the gap between the two consecutive slabs. Now, for your results, you need to derive the coefficient of volume expansion for copper, brass, aluminium, and to show your calculation. We know that we have this expression for linear expansion, delta L equals L alpha T delta T. We know that we have a relationship between the linear dimensions and the volume. So all you need to do, you need to convert from one-dimensional system to three-dimensional system. Okay, and to obtain an expression where you have, instead of delta L, delta V equals V times whatever the coefficient is, delta T. Okay, so you need to derive this expression. And that's it for this lab report.